Right, we move now to the next section, which is the force between parallel conductors, and you'll find this section in your book just after, it's on page 3. Sorry, page 7. Okay. I'm going to do this part, and then I'm going to split you into small groups and take you down the back, and I'm going to show you how the motor effect is used in both the galvanometer and a loudspeaker. So that is why we jumped forward. So we did up a period today. We're having a bit of a track as well. Okay, we now know that a current conductor in the presence of a magnetic field experiences a force. What is that principle called? It is called the motor effect. It is in fact the definition of the motor effect. It's the first half of our definition. A current conductor in the presence of a magnetic field experiences a force, and this force, the second part, is at right angles to both the magnetic field and its direction of current. Now, we now know that part, that if we take any current conductor and put it anywhere near a magnetic field, it will start to push or pull. What happens if I've got another wire? Around every wire, there must be a magnetic field. We know that. So two wires close by each other, which are carrying current, must push or pull each other away from each other. So this is called the force between conductors. To simplify everything, we're only going to look at parallel conductors. If we put them at angles, then it becomes a lot more complicated. So the course only requires us to look at parallel conductors. So that's what we're going to do. Okay, so here you are. Now this is space for you to draw this in your book. I'm going to explain it once, then I'm going to give you time like before to draw, copy and explain it to yourself. So in your book you said it says there to use a diagram to illustrate your answer, so you are going to draw a diagram and you are going to annotate the diagram. So once you draw the conductors, you are going to write around it and account for it. So it's not just going to be a drawing with some words beside it, it's going to be a drawing with you explaining the drawing. Okay, so here is the basis of our explanation. The basis of our explanation is we've got two wires, and just for simplicity, we are going to have them carrying a current in the same direction. So there they are. You can't see where they're connected to the power point or the electricity, just we've got two little sections and they are parallel to each other. We are going to hold one fixed. It doesn't matter which we hold fixed. Okay? We've just gone through a whole series of things looking at relativity, and special relativity especially, but going back just to the principle of relativity, it says that in an inertial frame of reference, the reference frame, whatever's moving reference to the other, is equally valid. So if I hold this one fixed and look at the second one over here moving, it's the same as holding this one fixed and looking at this one over here moving. Okay? Because they're equally valid looking things. Right, so we're going to hold this one fixed and we're going to allow this to move. Right. Now, looking at this one over here, I'm just going to write out that current I there for a few seconds so it makes a much nicer look. Because it's got a current going up, using our right-hand solenoid rule, which is your thumb pointing up, these are the fingers, okay, that's the wrong hand, that's the left hand, so you can do it, it's the, that's the thumb goes there, and it goes that way, okay. Okay, so they're fat fingers. Using your right hand grip rule, we know that the magnetic field around this wire here, which has a current going in that direction, is in a circular pattern around it in this way here. Okay? Are we okay with that? Now, drawing it, you just discovered that drawing things in 3D is a pain. It really doesn't help your cause when you try working things and pushes and pullings. So what we're going to do is we are going to use dots and crosses to represent on either side. So rubbing that part out now. Yeah. And let's get rid of our thumbs as well. We know that the circular magnetic field comes out of this side over here. Therefore, that would be a dot. And that is a half loop, comes to this side over there where it goes into the board and goes through the board and out. So that's part you're seeing a circle side on. It's coming out here, into there, going underneath the back and coming back. So all of these would be dots and crosses. For every dot, for every dot there'd be another cross, dot and a cross, making a circular loop. That's the first row. We know that this magnetic field goes, let's make it nice and neat. And we'll put a few rows on. I'm just going to put 5 rows, just enough to get past this other one. Okay. So we're not looking at the magnetic field around the second conductor, the ones that are able to be moved. We're looking at the magnetic field around the one that we're holding fixed. Are we okay with this? Please remember, I can repeat this at any time with the one that is held fixed. Sorry, allowed to move, and hold that one fixed. Right, now, all we are now going to do is now we're going to look at the second conductor, this one over here. And we know that it carries a current in that direction, and also it is now in the presence of a magnetic field that's going into the board. So using our FBI push rule, using our 3 fingers, we go, thumb points up, B points into the board, and we have the F pressing this way. I'll go nice and colour that way. F is pushed that way. Okay, are we doing that? Everyone got the idea that that conductor will be moved. Okay. Now, applying Newton's understanding that for every action force there must be an equal and opposite reaction force. If this one is no longer held fixed, but is allowed to move, and this one here is pushed this way because of a force, this over here has to have an equal and opposite reaction force, and it will be pulled in. Okay? So this would also be pulled that direction. And they would be equally and opposite pulls, as long as the current in both of these wires is the same. Okay? Now, if you didn't like that explanation using Newton's third law, you could just simply now hold this one fixed over here, this conductor, and repeat this, allow this one to move, and you'll find that it would move in that direction. Okay? So what happens is if the currents of 2 wires are running in the same direction, we get an attractive force between them, which goes against all of the ones that we know. Normally we say like poles or magnets repel, like charges repel. It's like currents attract. So 2 wires running parallel with a current in the same directions will be forced inward. Okay, we pull together. We can then just use common sense and say, well, what would happen if I now make this second one over here have a current, let's go different colour than pink, because let's go green. Imagine, that's a terrible green, the current now in the second wire, which is allowed to move, goes down, then we would know that the only thing that would change would be the magnetic field from this wire stays exactly the same, but now the current in this one is able to go in the opposite direction, using our FBI rule, we simply find that the current goes down, so it'll be pushed that way. Okay? Using Newton's third law again and allowing both able to be moved. If you push to the right, then you must be pushing off something. So therefore this would also be pushed away. Okay? So to the right, yeah. So if they are running in opposite direction, so one up and one down, we get a repulsive force. Okay. So in quick summary again, so because you're going to take this in a few more moments and you're going to draw it and annotate it. Remember the word annotate in the HSC, or illustrate is often used, means that you must use a diagram and add words to the diagram with arrows and in sequence and order to make a coherent statement to explain. In this case, you have to account. So, going through and highlighting the most important parts of your explanation. Apart from drawing the two, and we have them with the same current in the same direction to go with first, okay, you must indicate one is held fixed. It's from that held fixed that you would then be able to work out the magnetic field, okay? The magnetic field has to surround the second wire over here, the one that's allowed to move. And we look at the motion of the one that's allowed to move. And in either case, it will be going towards if they're in the same direction or away if they're going in opposite directions. Then you have to apply either Newton's third law for every action force, that'd be equal to opposite reaction force. And if you're still not getting that, just remember, a good way of looking at it is if we were thinking about the Earth and the Sun, and we just take the Earth and the Sun, there's the Earth and the Sun. The Earth is pulled towards the Sun by gravity, but remember, is the Sun pulled towards the Earth by gravity as well? Yes. These are also equal and opposite reaction forces. So this is the same thing here. If this wire here pulls this wire over here towards it, then this wire over here must be pulling this wire at the same rate. Are we okay with that? So it's very similar to the same idea that Newton came up with, equal and opposite reaction forces. Then you can, if you don't like that, you can just simply make the other one fixed and the other one allowed to remove. You can reverse the whole process, it takes longer. And then you come up with the idea that if the two currents are in the same direction, they are attractive. If the two currents would be in opposite directions, you would be repulsive. Now you don't need to do the experiment, you don't need to do two diagrams to get the second one. You just say the only thing different in the second scenario would be the current is in the opposite direction, and therefore using your right hand push rule, don't call it the FBI rule, that's our way in their class here to quickly reference that rule. So the right hand push rule, you would be able to see it go in the opposite direction. Okay? Take a few moments now to write that up. Now that we understand that there exists a force between two wires travelling in a parallel direction, we can then just nut out the actual formula. But I'm not going to go through the proportionality statements to get this formula. We're just going to give it to you. So here is the one. This is the one that's actually on the HSC formula sheet, that one there. And this is the one that most of us use in working with this thing. The only difference is that this thing there, the L, moves from up there to below there. Okay? And let's just identify what these things are. So I'm going to use this one over here. Oops. I'm just going to give the annotations. We know that this is the force between the two wires. And remember, they've got to be current carrying conductors, okay, and it will be measured in newtons, obviously. And I say that because of the reason of the other equation. I, as we know, these two here are the currents in both wires. Okay? So we know that there are two currents here. They don't have to be the same current. So I1 and I2 are just the two currents. L is the length of the wires that are in parallel. So it's the length of the wires in parallel. And it must be in metres. It's not in kilometres because there are quite often it's going to be in kilometres because parallel wires run for kilometres in parallel outside in the real world, taking stuff from power stations to us. And the last part here is, and this is where a lot of us, and me included, I keep on doing it, that's distance. It is not distance squared. We are so used to seeing on the bottom of these formulas, it's very similar, as you can see, to the gravitational one, mg on r squared. It looks like that, doesn't it? But it's only r on the bottom. It's a single distance on the bottom. Okay? So just be careful. And that distance, once again, must be in metres. The force, as you can imagine, gets really, really big the closer these two wires come together. Right, the last thing over here, which is new to us, is K. That thing there. Very similar to G. G over here in this formula, that's a gravitational force. That has 6.67 by 10 to the minus 11. Okay? And that's called the constant of gravitation. K, unfortunately, is not given a nice letter. It's just K. K is the constant of magnetic magnetism. I'll say it, permittivity. Okay? So it's just the magnetic constant. So it's 2.0 by 10 to the minus 7. Okay? That occurs, don't set these numbers to memory, that occurs on the data sheet. Okay? The magnetic constant of permittivity. Okay. It's just how much the magnetic field can penetrate space. That's all it's trying to measure. Are we okay with that? Now, what does this formula over here do is often we don't want to work out the actual force between the wires. Okay. We want to force this one over here on the other side gives us the force per metre. Okay. So if you are asked to find the force per metre, it just means that we're talking about using kilometres of wire, and we don't want to work out that there's a billion newtons between these two wires. That's just because they're very long. So we want to know what for every metre there is 5 newtons, so it's 5 newtons per metre. Okay. So we use this one over here when we want to work out the force per metre. And it's used in two contexts. When you're actually asked to work out the force per metre, okay, newtons per metre to the -1, okay? Or secondly, they don't give you the length. So we use this formula over here when the length is not given, and then the answer is in force per metres, or when you're actually given the length and you're asked to find the force per metre. Okay, and they actually say in the question, find the force per metre on this. Okay? Okay. So the difference is this formula gives you the total force on all of wire. This one here is the force for every metre of wire. That's the only difference. Okay. Now, looking at this one here, that's the actual overriding equation, this one here. Top, we know that we have a variety of proportionality statements within it. We know the force is proportional to both currents. We know the force is proportional to the length, and the force is inversely proportional to the distance. Okay? So we know that if we increase I1, the force will go up. If we increase I2, the force goes up. Okay? You'll find that there are 4 proportionality statements that you can fill in. One of them is, there's 2 ones for the current. One for I1 and one for I2. Okay? If the wires, the longer the wires run in parallel, the more force total, sum force on the wire. And the closer they come together, the greater the force. So as the distance goes down, the force will go up. Okay? Now your job tonight will be to work out why this happens. And it's on that box there, it says the effect of the change. Oh no, it just says the effect. So we don't care. You don't have to explain why. So in that box is just what happens. So if the current goes up, what goes up? Force. If the current goes down, the force goes down as well. So the effect of the change of it is increasing current increases the force, decreasing current decreases force. Okay? Length. In that table, if the length increases, the force increases. So increasing the length of the length of the wire that runs in parallel will increase the total, or the sum of all the forces on it, and vice versa. And the final change is just remember, if we decrease or make the wires come closer together, the force increases. We bring the wires further apart, the force decreases. Okay? So you can fill that in just out of proportionality statements. And finally, on the next page, on page 8, are 2 graphs, or 3 graphs that you have to fill in using the formula itself. Okay? Now the first one has F. Just see if I can move these up. The first one has F in this position, and current is in this one. It doesn't matter if it's I1 or I2, it's just current. Okay? Everyone found the graph? Now we have F is proportional to current. What would a graph look like if I had to draw a direct proportionality statement? Right, it's a straight diagonal line, isn't it? So you just simply draw that. In other words, it says, as I increases, so does F increase, and it's at the same rate. So if you double the current, you double the force. Triple the current, you triple the force. That's what a direct proportionality is. Okay, so direct proportion. Okay. So these graphs are very, very quick to sketch. The second graph is drawing a graph where it has force still on the vertical axis. Let's get rid of all that. Force still here. This time we have the length of the conductor on that. And because F is still proportional to L, it's a direct proportionality, we would once again get a straight line. Okay? Are we okay with that one? The last one, however, is a little bit more difficult. The last one has force. Oh, actually, I'll clear those off rather than that. We're asking that it's a force on this and distance on that. Okay? we know that the proportionality is F is proportional to 1 on D. Now, you've all done enough mathematics in either 2 or 3 unit extension to know what shape a y equals 1 on x shape is. It is an hyperbola. Yep, it's a hyperbola. So the shape would look like that. Okay. So that's a 1 on D shape. It's a 1. Remember, if you ever have to do a inverse square, if you get something like F is proportional to 1 on R squared, it's the same shape except much tighter. The hyperbola is much closer to the origin at its in this point here. Okay? So it's just a skill that you have to be able to do, is to draw very quick sketches of these. Okay? And last on that diagram there is conductors carrying current in the same direction are attractive. Okay, so if you see two currents walking down the road in the same direction, you go, woo, they are very attractive currents. Okay? If they are walking about down each other, eyeing each other off, they're probably going to repel each other. They don't like each other. Okay? So walking together, holding hands in hand, walking away from each other, they're repelling. It's the only way I can do it. Okay? Or you remember it is the exact opposite of everything else. Okay? Like charges repel, unlike attract. Like poles repel, north repels north, south repels south. But currents are exactly the opposite. Okay, that's the only one I can remember. I keep on forgetting it. Okay, and I often have to fiddle around. Are we okay with that? Right, now on your table, you have got the motors and generators worksheet 1B, which uses these forces. Okay, I'm not going to actually give you examples, I'm just going to let you use it and try and sort it out yourself. Just remember that in all cases here, and I don't know if I typed at the top of that sheet, K is 2.0 by 10 to the minus 7. So I did that? Yep. Now, why is it 2.0? Why is it just 2? It's telling you that it's correct to two significant figures. Okay? But you can just type in the calculator as 2 by 10 to the minus 7. Okay? Have a go, they get progressively more difficult. After you've done that, you can then do question 4 through to 11, pages 4 through to 11. That will get you up to talk. Okay, so they're all past HSC papers, you can see them. So do the sheet first. And then pages 4 through to 11. Okay, thanks.